Hello and welcome to our second webinar presentation by the Underground Construction Association Young Members Group. If this is your first time joining us or you missed the introduction in the first webinar, I'd like to begin by introducing you to our group. My name is Erin Clark and I'm one of the 3 members of the new UCA of SME standing.
Yes, hello.
For the UCA Young Members. I'm the Professional Development Chair, and I'm joined by Anthony Bauer, the Chair, and Shannon Goff, the University Outreach Chair. The UCA Young Members are a group of professionals and students of all ages with a common interest to grow and develop the population of engineers and construction professionals under the age of 35
Is that better?
within the underground industry. Throughout the year, you can join us for monthly webinars and stay involved in the conversation by visiting our website at community.smenet.org/UCAYM. On the website, you are able to gather more information on the group, and we encourage you to become a member of the group and of UCA of SME in order to take advantage of the many benefits the SME and UCA communities offer. At the annual RETC NAT conference, we will host a networking event for students and professionals under the age of 35. Our monthly webinars will be hosted on the last Wednesday of each month. Next month, join us on April 29th to hear 2 students from the Colorado School of Mines discuss their current research projects. Today, we continue our webinar series with a presentation by Eric Wang on overcoming the challenges faced on the construction of the MTACC'S East Side Access Project in New York City. Mr. Wang is Associate Principal for Tunnels, Manager for the Geotechnical and Tunneling Group at Jacobs Engineering. He has 26 years of design and construction experience focusing on geotechnical and tunneling engineering for transportation infrastructure projects, including 6 years with the construction contractors, 4 years with geotechnical sub-consultants, and 6 years with prime engineering consultants. Eric specializes in permanent rock anchor systems and ground improvement techniques for underground structures. Eric has been in the project and operational roles in projects located in the United States, Canada, and Germany. Eric is a strategic outreach community member for the UCA of SME and is also affiliated with the MET section of the ACE and the Deep Foundation Institute. Thanks for presenting today. When you're ready, please share your screen.
Welcome and good afternoon, everyone. Thank you for joining today's webinar entitled Overcoming Construction Challenges on MTA Capital Construction's East Side Access Project. My name is Eric Wang, and I'm coming from Jacobs Engineering. This slide is a brief background. I'm originally from Montreal, and I earned a bachelor's in engineering and civil engineering, as well as a MEng in mining engineering from McGill University. Began my career working for a tunneling contractor in 1989, working on $3 million drill and blast tunnel job, a connecting tunnel under the St. Lawrence River that also featured shaft sinking and tie-in to an existing plug to the Southern Interceptor. That was my first tunnel construction project, and I was with that contractor for about 3 years. In the late 1990s, things started to slow down in the underground industry, in Montreal in particular, and I relocated to New York to join the Geotech and Tunneling Division at Parsons Brinckerhoff, worked on several tunnel assignments such as New York City DEP's New Croton Aqueduct. That was a pressurization study. There was the Cumberland Gap Project, New York City Transit 63rd Street, tunnel connection, Cleveland Hilltop Interceptor, as well as another light rail project, Portland West Side Light Rail Project. After 6 years in tunnel consulting with PV, I moved to New Jersey to work for small geotech consultant, primarily retaining walls and foundations. Was in New Jersey for through to about 2000. And then in 2000, I joined another prime engineering consultant working primarily on bridge projects in New York City. And then in 2008, after 17 years of design, I returned to underground contracting with Judd Love Contracting, working on the East Side Access Project, which is the subject of our webinar today. Since 2011, I've been with Jacobs Engineering, based out of New York. Okay, just a little brief rundown on how I got started in tunneling business. My father was bridge structural engineer for CP Rail and encouraged me to pursue undergraduate degree in civil engineering. And from there, general civil engineering courses, and I began a master's in 1988 in mining underground. During my first interview, one of the interesting questions that came up was, what was my real career goals and my interest? This is the tunneling contractor that I began working with. Mentioned my background with civil, general civil background, as well as my interest in underground construction. And so there was a connection, since he had previously been working for Atlas Construction. He was a tunneling veteran, working on a lot of global mega projects, overseas assignments. Okay, let's go right into our project, our discussion today. This is this map gives a little background on the purpose of the project. Basically, it's a connection, a commuter rail connection from Long Island, basically Long Island Railroad, taking commuters into the east side of Midtown Manhattan, using the lower level of an existing 63rd Street tunnel to beneath the East River, and proceeding south beneath Park Avenue, tying into a new station facility beneath Grand Central Station. Okay, some of the key features on the project. This is a very complex underground project that involved 8 TBM running tunnels, 10 Wye Cavern bifurcations, as well as twin main station caverns, 1,200 linear feet, 60 feet wide by 60 to 65 feet high. And what we see here in the upper right-hand corner are some of the challenges that we had to overcome. The shallow cover under subway crossings, existing subway crossings, and we'll go into some of the challenges that included multiple TBM backup and relaunches, as well as mucking from the heading in Midtown Manhattan out of a mucking shaft located 3 to 4 miles away in Long Island City, Queens. Okay, some basic description of the project. Talked about the 8 22-foot diameter TBM tunnels for a total of just over 32,000 linear feet. Cover range from a minimum of 45 to 140 foot depth. So some of the key dates on the project. It actually involved 2 contracts. The first contract was running tunnel, CM009 Manhattan Running Tunnel. The notice to proceed was June 2006. And the first TBM, the Selly TBM, was launched September of 07, the eastbound drive, and it was followed a few months later with the main being Robbins TBM in the westbound tunnel. There was the notice to proceed a year later, May 2008, for the cavern structures. And substantial completion was June 2013. Basically, my role was twofold. Geotech engineering manager for Judlow, that involved working on as a design liaison between the GEC, the PMCM, our various design subconsultants, and also providing technical oversight, in particular for the excavation initial support design. Then in the latter half of my stint, I was involved in the swing shift as a project engineer, overseeing specific operations including cross passage, drill and blast excavation, roadheader enlargements of the TBM tunnel, pre-support in shear zones, and the topic that we're going to discuss in more detail is the replacement of ribs for TBM backup, as well as launching and TBM relaunch using the concrete plug concept. So this isometric view just gives you an idea of the basic layout of the project. We're starting at this end of the project with assembly area, the beneath 2nd Avenue that we launched the project from. The TBMs were launched through there. Then from there you have upper level tunnels that connect into GCT3 Wye Cavern, and lower level tunnels at GCT4, as well as the main station caverns between the two Wye Caverns, GCT3 and then GCT1 and 2. So just want to give you a general idea of what we had in mind, what the scope of the work was. So our webinar is going to concentrate on 3 key challenges broken up into the expediting the relaunch of the TBMs using the concrete plug concept and why we had to do that. Some of the challenges with muck handling, muck conveyance. As I mentioned, 3 to 4 miles away, we had the mucking shaft from the heading and dealing with various types of muck, shot rock and drill and blast, as well as roadheader fines and TBM muck. And also to permit backup of a fully assembled TBM, we're going to discuss how we overcame the rib replacement sections that had existing steel ribs. So let's begin with the relaunch of the TBM. Again, mentioned multiple TBM drives, backup and relaunching operations. What we're showing here is the, in red is the Wye Cavern area, where we had to back up the TBMs, create a starter tunnel with a road header, and then relaunch through to the next, to the subsequent drive. And then we'll look at why that proved not to be feasible in terms of construction schedule. Looking at some of the excavation options that we had to choose from, conventional drill and blast were available, road header as well as TBM. In the area that we're going to be discussing, the blasting restrictions made it very difficult, so we had to look at alternative excavation methods. So here we're looking at the mining sequence that was used in the initial Wye Cavern enlargement. This is over on GCT3 eastbound. We used the road header. You can see the road header in these 3 different sections, the small, medium, and large Wye Cavern section. You've got the road header mining, enlarging the existing TBM tunnel. You've got over here, you've got the drill jumbo installing the initial support. Drill jumbo installing the initial support. And then you've got the scoop tram working on mucking out the heading. Okay, here, this cross passage, as we mentioned, we looked in plan view, we saw the small down here, medium, and then the large Wye Cavern sections. And what I'd like everyone to focus on is you see the ramp, the muck ramp that we had to create in the medium and large Wye Cavern section. And the purpose of that was to provide access for the road header so we could reach the arch, excavate the arch, get access to that. Okay, talking about some of the specific construction challenges with the road header, some of the material that we encountered at GCT3 eastbound proved to be very abrasive amphibolite, in particular below the spring line, that generated extensive wear on the picks, so a lot of delays with changing out the picks on the road header cutter head. And what we ended up using, the solution we ended up resorting to resolve that is chemical expansive additives. The damite was used. We drilled holes to insert the damite so that we could essentially soften up the this hard abrasive amphibolite to facilitate road header excavation. Also very time consuming. Another consideration that we had with the road header option in developing the Wye Cavern is we had to create a starter tunnel in order to launch the TBM. And what that entailed was the reinforcement of the existing narrow pillar. You see this narrow pillar here? We used pre-stress through bolts number 9 Dewey dag, pre-tension to 15 tons on a 4x4 pattern. That was the stabilization method used for the pillar. As well, you can see up in this area, we also included channels to help stabilize the areas where the grippers would be launching out of the starter tunnel. So here we see a photo of the drill jumbo working from the completed TBM drive, the initial TBM drive, and installing the through bolts, pillar reinforcement into the starter tunnel. Here we see mining of the starter tunnel in progress. You can note up here the mine straps that we used to provide protection of the brow. Here, another lengthy operation with the initial roadheader option was to set rail, pour a flat invert, and to set the TBM cutter head on rail-mounted dollies, backing it out of the existing tunnel drive, and then here we see it advancing into the starter tunnel. So in summary, some of the difficulties with the roadheader, you can see the extensive duration, talking from August 08 to March 2009, approximately 7.5 months. Excavated about almost 6,000 cubic yards. Broke down into about 70% with roadheader alone, solely the roadheader, and remaining 30% needed help with the damite, as we mentioned, the harder material, the amphibolite that was encountered below the spring line. And this is a big number. The delays as well as the material cost of these excessive wear on the picks and the changing out of the picks. So based on all these considerations and the need to accelerate the construction schedule, we had several VE sessions with the GEC as well as the program management and construction management team. And some of the constraints that we talked about, we had to incorporate into any brainstorming solutions were the existing geometry that was fixed, what the ground conditions were these favorable ground conditions, or any options that we would be looking at to accelerate the relaunch, obviously the schedule. So based on these multiple discussions, these VE sessions, we the outcome was the concept of the concrete plug, which we'll talk into a little more detail. So start with the initial concrete plug, which was a cellular concrete mix with the basic objectives of really trying to optimize the concrete volume, minimize how much concrete, because this is a temporary plug, keep in mind that we have to mine out later. We already want to maximize the amount of rock excavation. You can get a lot more effective rock excavation using the TBM than obviously the very slow roadheader, and then drill and blast was not an option because of the restrictions below Grand Central. And obviously the main objective is to get on, relaunch that next TBM drive, and we looked at options that could help accelerate removal of the remaining plug within the Wye Cavern. So let's look in a little more detail. Here's the layout. So here what we see is the existing tunnel. That was the outer tunnel. This is heading down into the station, so you're going north to south. This is the location where the concrete plug was poured. And then here, this second drive, that's the TBM that mined through there. And what you see here is you extended the concrete plug still within the Wye Cavern, but you had to extend it to a certain point where we achieved the minimum pillar thickness. So that's why this extra was, the temporary concrete plug was extended to this point to get that minimum pillar thickness. And this later, being temporary, would have to be mined out with the roadheader or various excavation options. So again, what I want to show here was a comparison of what we did over on the eastbound side using the slow roadheader, 7.5 month duration versus, sorry about that, versus what we are trying to achieve with this new option, the concrete plug. pouring the concrete plug in the existing tunnel and accelerating the TBM Re-launch. So let's look in a little bit more detail what we did. Okay, so here this is the cross section to give you an idea of the various sections within the Wye Cavern. You know, keep in mind these are the limits of the Wye Cavern that we have to achieve. What's important to see here is these are not the typical bolts that we have for the running tunnel. This is an area where you're going to enlarge the TBM running tunnels to bifurcate in the Wye Caverns. So these are longer bolts that we have to install. So obviously they had to be installed in the existing tunnel prior to the concrete pour. And then in the subsequent tunnel, we install that after the TBM was relaunched. Another important consideration was how would the main beam hold up, the main bearing hold up under this mixed face condition. You got some rock as high as 14 KSI unconfined compressive strength versus a cellular concrete at about 1 KSI. So obviously this uneven loading would have to be considered, and we how we consider that, we did an analysis of the maximum overturning moment that the main bearing was designed for and compared that with this situation, the what we call mixed face condition. And with that, we were able to back calculate and figure out what the limit was on our thrust on each of the disc cutters so that we would avoid damaging the main bearing. Okay, and another interesting note I want to bring up is some of the construction difficulties with the concrete plug that we addressed in subsequent refinements of this concept was when we had the spalling. This is an area where the grippers are pressing against this cellular concrete, and without confinement at the top of the concrete plug, we experienced the spalling, and to such an extent that there was actually damage. We had, I believe, 7 days of delay as we had to repair the gripper shoe that had been damaged because it was no longer supported. So what we did to address that, in these particular areas where spalling became an issue, we installed on the top of the concrete, this temporary concrete plug, we put some additional timber cripping to provide some confinement, and obviously try to minimize the gripper forces. Okay, the last piece of the plug option, as I mentioned, this is a temporary reinforcement of the existing pillar to allow expediting the TBM Re-launch. So obviously we had to remove that to allow excavation, continued excavation within the Wye Cavern to open it to the final cavern limits. Okay, so we talked about various refinements and variations of the original concrete plug concept, basically lessons learned, if you will. Concept number 2, which was back at GCT5 westbound, we said, hey, listen, with that cellular concrete mix, we've got a lot of issues with the spalling, so we really focused on something that provided high early strength, self-leveling concrete mix, but also realizing that we'd have to subsequently remove this temporary plug. We also looked for something that wouldn't have would have a reasonable 28-day strength to facilitate removal. We also want to reduce the concrete volume. Obviously, removal depends on how much concrete you put into that plug. So one option that we looked at is taking up some of the volume with this bladder, this water bladder that was secured to the invert, filled with water, and take up some of the volume. As I mentioned, concrete removal, plug removal was a concern, so we came up with this innovation of an arrangement of vertical PVC piping that provided access. You know, after this is poured, now we have access to install the damite, you know, to facilitate breakup of that and subsequent removal of the plug. So here we see some action photos. You've got the emergency catwalk up here, to provide access all along the concrete plug. See the pour and then the post-pour after stripping. Okay, moving right along to another concept we came up with on the concrete plug is we were pretty happy with the concrete mix, but we really want to accelerate removal of the plug. And here we also looked at how we could accelerate direction of the form for the plug. And so what we did is before we backed up the TBM, we created drill and blast niches. These niches were storage niches that accommodated two things. They accommodated the formwork for the bulkhead for the concrete plug, as well as the dollies for the cutter head for backing up the TBM. So that was very helpful. And the roadheader excavation of the plug, you'll see that more clearly why we needed to do that on the subsequent slide, the layout. So here we're looking at, it's very sensitive, the mouse, but here's the plug, and then this is the subsequent TBM drive. And so what we are trying to do, here you see below, we're creating a ventilation bulkhead so that we can isolate and perform the roadheader excavation. Why we needed the roadheader excavation, once the TBM passed this point, we started working back here using the roadheader to mine out a little access way so we could provide access to the miners to perform drill and blast excavation of the east-west adit further on. So we didn't have to wait until this plug was completely mined out. We just used the roadheader to create a little access way here. And also, that obviously was much faster than the hole ram that we saw before. Okay, so really, this concept number 4 is our last opportunity to use the concrete plug option. It was that GCT4 crossover, and what I wanted to show here was how we used a ventilation bulkhead that was installed while we were mining. So, let me go back. While we're mining here in this new tunnel, in the relaunch tunnel, and this is the area where we had the existing tunnel that was filled with the concrete plug, what we're doing is up here we're creating these partial ribs, if you will. And you got to keep in mind that as you see in this photo, this is mining through the plug. It's not uniform. The opening that you have, it starts from very small to gradually increasing, and you can see that more in detail here as you start at the end where you're starting to break out daylight out of the plug into the new tunnel. You still have that minimum pillar thickness that we talked about that gives you the limits of the plug. And what you're doing here essentially is you're using this partial rib idea to prepare a dust curtain, if you will, a cutoff wall so that you could work independently. The roadheader could work over on this side, with the protection, the ventilation bulkhead protection, and then TBM could continue mining. So actually, these were installed at the back end of the TBM. So these are some of the innovations that were used to expedite the GCT4 crossover cavern, as well as launching the TBM. Okay, so let's look at what we learned from this whole exercise. The importance of expediting TBM relaunch. Obviously, we couldn't continue with the number of relaunches that we had. We couldn't continue with the slow, tedious roadheader option, and also be prone to excessive pick wear if we encountered some of that hard amphibolite. What you did with the relaunch, you also had an opportunity to mine more of the Wye Cavern limits. It's more productive to mine with the tunnel boring machine than these other methods. So if we could incorporate that into the overall plan, that was a plus. And obviously, you keep in mind this is an urban setting. This is under Park Avenue. So any reduction in drill and blast excavation is viewed favorably by the client as well as the surrounding residents. And with the plug option also, lesson that we learned from that is it's a nice flexible option. The flexibility in that concrete plug concept provided multiple options for removal as well as performing simultaneous operations. Okay, the next topic that we need to cover and is some of the challenges with the mucking. Now, here are some of the photos of the vertical belt. Keep in mind, the mucking shaft is all the way on the other side of the East River in Long Island City, Queens, out by Northern Boulevard and dumped into Sunnyside Yard. I don't have those photos here, but we really needed to overcome inefficient mucking because you had a mix of shot rock as well as roadheader fines and TBM muck. You had the logistics with the top heading of the main station cavern filled with shot rock. You had the extensive cavern dimension. Keep in mind, the original mucking scheme worked very well when we were working on CM009 contract, when you're just dealing with a linear TBM running tunnels. But as we mentioned, 2 years in 2008, we started the second contract, the caverns contract, that included shot rock, for the cavern excavation. So basically, we had to revisit that overall mucking scheme, and that's what I want to talk about. Okay, mentioned the difficulty with muck-bound top heading. So here you see that situation. You also see the restricted headroom that you have. And I'm going to show you in some of the subsequent slides why this is a problem getting the traditional conventional muck cars up into this top heading. What were some of the constraints? So talking about the multiple excavation types, you've got active TBM drives here in red, on either side of the main station cavern. You've got road headers working at the top heading, as well as beginning at to enlarge the lower TBM tunnels. And then you've got drill and blast as well, drill and blast of the cheeks that we had to be performed. So what you're dealing with is various types of muck, not all of it conducive to the regular TBM conveyor belt. So here we see a cross-section of what we have to deal with in section AA, taken through the cavern. You have the top heading. See a lot of that shot rock here. That created difficulties. Couldn't put it on the belt. We needed to use the muck trains where it was available. And then here is the basic cross-section. You've got the road header working in the lower level, and then you had the drill and blast finishing off the top heading excavation. And here, these were the available tunnels for the rail. But the difficulty with using these for mucking is the availability of these rail tunnels were limited because you're also using that to bring in material for the top heading. We had to, at the same time that these headings were being excavated in the main station cavern, we had to quickly install the arch waterproofing as well as the reinforcement. So that also took up some of the availability of the rail that we needed for the muck cars. Okay, so the solution to all this, and we talked about some of the large shot rock that we had to deal with, is using a crusher. This jaw crusher system we installed in within the future Wye Cavern limits, and this allowed us to process the shot rock and allow it to be placed onto a transfer belt and incorporated into the regular TBM conveyor belt system. And here I want to show this photo of the extra 3.5-foot pit that we had to embed the crusher in so that we could accommodate the load haul dump. The load haul dump couldn't reach the feeder point. It was a little too high, so we had to depress that. And over here, what you see is some of the configurations that we had to use on the discharge conveyor belt. We had to raise that so that you could still have the vertical clearance of bringing in the man trips and using that rail. So here we see overview of the crusher as you come into the station cavern. So the initial crusher was in the top heading, the location, and then when that top heading excavation was completed, it made sense during the bench excavation to relocate that crusher downstairs so that it could facilitate processing of the shot rock from the benching excavation. Okay, so just in summary, some of the reasons that muck trains could not be used, and we had to augment the mucking system with the crusher and the various belt configurations, is that we only had one crane over at the mucking shaft. So whatever muck cars came back, they had to wait their turn. We had a tail track that could accommodate, I believe, 1 or 2 muck cars, but not much more than that. Again, limited crane availability, limited geometry, to load the trains. We talked about the low headroom situation at the top heading. Rail availability, again, is a concern. So the crane availability, limited rail, low headroom, and inability to meet schedule stayed with that original mucking scheme. Okay, the last construction challenge that I want to touch upon is rib replacement. Now, why did we have to look at rib replacement carefully? Is because we had, as I mentioned, 2 types of TBMs. One is the Selly double shield that did not have a collapsible cutter head feature. So the problem with this is we could not reduce the cutter head and back it out of ground class 3 conditions where we had all this existing ring steel. So we had to come up with a scheme that could replace this ring steel. And also we had to look at ways to leapfrog the existing ring steel where we had mandatory steel sets had to be put up where we had shallow cover over subway crossings. And then obviously any system had to be proof tested. Okay, so we started out by identifying the areas where ring steel would be interfering with the TBM backup operations to allow TBM to back up and relaunch. So these 5 locations were areas that we actually visited as a team, each of these locations. Bear in mind, some of this ring steel was installed based on the contract drawings that were designed based on the existing test boring information. But now we had an opportunity for revisiting the TBM board, the completed TBM board, and seeing what that actual ground conditions were like, and to see if there were some opportunities to upgrade some of the support classes. Also, I didn't include the slides, but some of the locations were fallout zones, like this cathedral void, areas where we had shear zones, Christmas shear zone, and I'll go into some of the solutions that we had. Okay, again, I mentioned there's some areas where we had mandatory sets had to be installed. So even if we backed up the TBM, we had to leapfrog and reinstall in front of the TBM, bringing your steel through the TBM and reinstalling so that you'd have that mandatory set under the shallow cover for the existing subway crossings. What was the approach that we used? As I mentioned, we had the existing TBM boards provided actual access to actual ground conditions. So we had the geotechs from the various parties, the contractor, the GEC, as well as the PMC and the CM teams, pay visits to these 5 locations where the steel sets had been installed and where they were in the way blocking TBM backup. And that provided the opportunity, as I mentioned, to look at the actual ground conditions and see if there's opportunities to perhaps upgrade or maybe update the ground support classes. So this was all done in a team environment with sessions, risk management workshops, where we reviewed the findings in the field and came up with sound criteria, practical criteria that could also be verified in the field. Okay, so we mentioned one of the systems in areas where we didn't have the mandatory ring steel and the ribs could be replaced, such as some of these fallout zones that we're looking at here. And look at this sketch that we have of basically takes you through the operation, starting from the mixing, the careful observation of the drilling and installation. You got to keep in mind that this is an area where we had sustained fallout. So in order to continue mining the TBM, we had to place backfill, cellular backfill. And so that provided a very clear indication. When you're drilling these MAI bolts, these self-drilling anchors, you can tell the difference in the resistance when you're going through the backfill compared to in the host rock. So the requirement was 10 foot of competent embedment, 10 foot into the competent rock. Then once we achieved that, then we proceeded in this step number 2 to inject grout through the MAI bolt. There was a sacrificial drill bit that popped off and allowed the grout to be injected, fully encapsulating the bolt. The pressure gauge indicating the this was the pressure gauge for the testing of the bolt, and then we repeated in the subsequent pattern that was designed beforehand, and then we provided the pull testing to verify. And any anchors that failed, we subsequently had to install replacement anchors that were also pull tested to verify capacity. Okay. With that, I want to move on quickly just to touch on, I was asked to mention briefly some of the career challenges. And I guess at the beginning of your career, you're really trying to define your strengths, where your strengths and your aptitude lies, and trying to match that up with a practical career that you'd enjoy. I mentioned that in 1991, things were getting slower in Montreal. Tunneling jobs were few and far between, and so I had to adjust to relocating the family to the U.S. at that point, to New York, where I was able to so far remain for the last 20 or so years. Want to also mention this may be at different stages of your career, but you're going to have to deal with the family and work balance with your various assignments. And the other bullet point I want to make too is the importance of considering, the challenges of projects, but obviously there's some sacrifice on the family end, as there may be some relocation involved, versus working in more of an operational capacity where you're working within a group in one fixed office location, but your involvement may be on smaller scale projects, or if you're fortunate on challenging local assignments. Okay, with that, just want to wrap up and summarize that personally I've seen I've been able to enjoy the tunneling industry for the opportunities to deal with many challenges, incorporate innovation, thinking out of the box. As you saw in a couple of the case history examples, basically this isn't textbook solutions. This is using some judgment, understanding the ground conditions, understanding what we're trying to do, what we're trying to achieve, and look at opportunities to optimize. Contractors looking at time and money. Time and money are paramount. And tunneling is also a very high-tech, progressive industry. There's a lot of software tools that are now available that help us with analytical problems, talking about some of the shear zones, looking at some of the ground support, some of the spiling pre-support that could be used, and opportunities to verify that and predictive models. Also believe that this career, tunneling, why I like it, it's very team-oriented. It's relationship-based. What I mean by that is on these projects, you're working side by side with key like-minded mentors, colleagues at the same experience level, or bring other facets of their personal work experience. And what you're trying to do is bring out the potential of everyone on that team to deliver the project, to deliver outstanding quality on that project. So I believe that tunneling provides that opportunity to work in a team setting. And also global opportunities, not just what we have here domestically. There's tunneling projects around the globe that, based on the skills that you develop early on in your career and some of the network connections that you also are able to develop, you can be in line for some of these opportunities to work overseas. I thank everyone for attending and for their attention, and we're moving on to the Q&A portion.
So our first question today was, what was the allowable surface settlement, and was the limit ever hit?
Okay. To be honest, I was less involved with the work at the Madison Yard and some of the work with the surface penetrations. I was more involved in the rock excavation, so I wouldn't be able to answer that question accurately. We did have some monitoring of and I didn't mention it in the presentation, but we did have monitoring of the ribs, during the rib replacement, to make sure that there wasn't excessive convergence in the tunnel. But in terms of surface monitoring, I know that there was seismographs installed before we did the shot in the cavern. Seismographs were installed in the existing yard facility directly above us.
Okay, Eric, it sounds like those are all of our questions. If anyone has any other questions, please make sure to email Eric. On his last slide was his contact information, Eric, ERIC, Wang @jacobs.com. There you go. Thank you for joining us today, and as Heather mentioned, the webinar will be available, the recorded webinar will be available in a few days.